Welcome, my friends! In this video, we will discuss the confidence interval for the difference in proportions of two independent populations. By independent, I mean that the sample observations from the first population have no impact on the observations from the second population. Let's say we are interested in the proportion of adults living at or below the poverty line in a given city. We may have sample 1, which reveals that 0.2 or 20% of Grand Rapids adults are at or below the poverty line, and we might have a second sample that reveals that 0.14 or 14% of adults in Salt Lake City are at or below the poverty line. We assume these samples are independent, as they came from different cities, and should not affect each other in any way. The quantity we are trying to estimate is the difference of two population proportions, P1 minus P2, and the point estimate is the difference of the two sample proportions, p hat 1 minus p hat 2, which comes to 0.2 minus 0.14 and equals 0.06 or 6%. The interpretation of the point estimate is that we estimate that the number of adults in Grand Rapids that are below the poverty line is 6 percentage points higher than adults in Salt Lake City. An example confidence interval might be 0.02, 0.1, meaning that we are C% confident that the difference in the proportion of adults in poverty between Grand Rapids and Salt Lake City is between 0.02 and 0.1. Notice that we can refer to proportions as either percentages or decimals. Both ways are acceptable. On a number line, the confidence interval would look something like this. The point estimate of p hat 1 minus p hat 2 is in the middle, which is 0.06. The lower bound is 0.02, and the upper bound is 0.1, and the margin of error is 0.04, the distance from the point estimate to either of the bounds of the confidence interval. At this point, I haven't shown you how to calculate the confidence interval, but we will look at how to do that very shortly. For two sample confidence intervals, there are three possible end results. If both values are positive, such as an interval ranging from 0.02 to 0.1, that means we are C% confident that the first population proportion is larger than the second population proportion. If both values are negative, such as negative 0.1 to negative 0.02, that means we are C% confident that the first population proportion is smaller than the second population proportion. If one value is positive and the other is negative, such as negative 0.1 to 0.02, we cannot conclude whether or not the first population proportion is larger or smaller than the second population proportion. Stopping to think about these rules, they should make logical sense. Take the first example. If the difference in sample proportions produces a confidence interval with two positive numbers, such as between 0.02 and 0.1, every single value in that interval is positive, suggesting p1 minus p2 is greater than 0 in all cases. The only way for p1 minus p2 to be positive is if p1 is greater than p2. Thus, the conclusion holds. The same kind of logic can be applied to the other two rules. Only when the number 0 is contained inside the interval, such as in case 3, can we not conclude whether or not the first proportion is greater or less than the second proportion. Thinking of our confidence intervals in this way is very similar to the results of a hypothesis test, which we will discuss in more detail in future videos. Here is the formula for the confidence interval of two population proportions. We have p hat 1 minus p hat 2 plus or minus z times the square root of p hat 1 times q hat 1 divided by n1 plus p hat 2 times q hat 2 divided by n2. Z is the positive z-score corresponding with the desired level of confidence. P hat 1 is the sample proportion from sample 1 and is equal to x1 divided by n1, where x1 is the number of successes in sample 1 and n1 is the sample size of sample 1. Q hat 1 is the proportion of failures in sample 1 and is the complement of p hat, or 1 minus p hat. The same idea follows for all terms with a subscript 2, except they come from the second sample. In order to use this confidence interval, n times p hat and q hat must be at least 5, both in sample 1 and sample 2. Some textbooks suggest they should be at least 10. This ensures that the distribution of p hat 1 minus p hat 2 follows a normal distribution by the central limit theorem, which is required in order for us to complete the test. Let's look at an example. Income data from 150 randomly selected adults in Grand Rapids and 200 adults in Salt Lake City revealed that 30 of the adults in Grand Rapids were at or below the poverty line, and 28 of the adults in Salt Lake City were at or below the poverty line. Construct a 90% confidence interval for the difference in the proportion of adults at or below the poverty line in Grand Rapids and Salt Lake City. Here is the formula for the confidence interval for the difference of two proportions. We can let sample 1 represent Grand Rapids and sample 2 represent Salt Lake City. N1 is the sample size in Grand Rapids, which is 150, and N2 is the sample size in Salt Lake City, which is 200. X1 is the number of individuals in poverty in Grand Rapids from the sample, which is 30, and X2 is the number of individuals in poverty from Salt Lake City from the sample, which is 28. P hat 1 is X1 over N1, which is 30 divided by 150 and is equal to 0.2. Which makes Q hat 1 minus 0.2, which is 0.8. P hat 2 is X2 over N2, which is 28 divided by 200, which is 0.14, which makes Q hat 2 1 minus 0.14, which is 0.86. Notice that the four quantities that we discussed earlier are all at least 5, which ensures that the central limit theorem applies, and we can move forward with the confidence interval. The confidence level is 90%, meaning that the graph has 90% of the probability in the middle and 5% in each of the tails. P hat 1 minus P hat 2 goes in the center, which is 0.2 minus 0.14, which is 0.06. The z-score in the formula is the z-score corresponding to the 90% confidence level, which we know from my handy table is 1.645. If you want to know how to generate this number from a z-table or a TI-84 calculator, check out one of my videos in the description. Now we are ready to plug into the formula. We have 0.2 minus 0.14 plus or minus 1.645 times the square root of 0.2 times 0.8 divided by 150 plus 0.14 times 0.86 divided by 200. In the TI-84 calculator, or any scientific calculator, we type in 0.2 minus 0.14 minus 1.645 times the square root, which we get by pressing second and then this key, 0.2 times 0.8 divided by 150 plus 0.14 times 0.86 divided by 200. Press enter and we get negative 0.0072, which is the lower bound of the confidence interval. Now we need to enter the formula again, but change this subtraction sign to a plus sign. On this calculator, if I press second, enter, I bring up my previous entry. Then I can scroll to the left and change this minus sign to a plus sign, and press enter to get 0.1272. This is the upper bound of the confidence interval. We can include the lower and upper bounds of the confidence interval we just calculated onto the graph. Our conclusion is that we are 90% confident that the difference in the proportion of adults in poverty between Grand Rapids and Salt Lake City is between negative 0.0072 and 0.1272. Since one value is negative and one value is positive in the confidence interval, we don't have enough evidence to suggest if there is a difference in the proportion of individuals in poverty in Grand Rapids and Salt Lake City. In other words, the number 0 falls within the interval, meaning no difference in the two population proportions is consistent with our data. Alright, my friends, we have finished our discussion of the confidence interval for the difference of proportions of two independent populations. We will be exploring many more fun and exciting statistical topics that you won't want to miss, so make sure to check out our other videos.